Hi, folks. Second day of Hadoop Summit, right? And this being the last session, let's see how we can keep this really interesting and interactive, I guess. So, I mean, like this is a really small crowd, but how many of you have been here at Hadoop Summit like last year? Okay. How about Hadoop World? Okay, so it's all new. That's great. Okay, so I'm Samuel Como. I'm one of the technical marketing engineers for Cisco's next generation switching platform. I focus on applications, profiling applications from a network perspective, and basically talk about things like, what are the best practices, recommendations that Cisco has in this space, especially towards the big data workloads. So that's my major focus, and I've been working with Hadoop for the last 4 years, since 2009, when it was still in its beta form, or whatever you call it, 0.18. So today we are going to take a look at some of the basic stuff within Hadoop, like how does it work and where do you find the most benefit out of Hadoop clusters. And we'll move on to some of the constructs that the latest next generation stuff that is coming from a network perspective. And we'll also look at a few recommendations and what works and what doesn't, and our own experiences. I'll share some of those. Great. So that covers the agenda stuff. So optimization, tuning, and some of our recommendations, and we'll hopefully have a Q&A session at the end. In case we don't get time for Q&A, we have a booth, P12. You could come down to our booth and we could have a discussion. We have a few more folks focused on UCS and Nexus platforms, so you could have a talk there too. So what have we been doing in this space? Since 2009, since the time we actually started working on this, right, I've been involved in this. We have presented at various Hadoop Summit, Hadoop Worlds before. We work very closely with partners like, I mean, both open source Apache, but also with Hortonworks, Cloudera, and MapR. We work with all these partners, Oracle NoSQL, if you've heard about that too. So we've been doing this for quite some time now. Moving on, Hadoop overview. So how many of you have a cluster and are familiar with Hadoop already? Okay. And I guess the rest of you are just starting off or something, right? So a very quick overview. It's not going to take more than 2 minutes, but basically the idea is this. And this is a 5-6 year back story where Hadoop started, right? Basically the idea is a single node cannot really ingest the terabytes of data that we are finding today in the web space, right? A single node, if you have to run it through something like a small Oracle appliance or something like that, right? It's not easy to do that at all, simply because of the bottlenecks that you have with the I/O. So what do you do with this problem, right? One solution could be you could increase the number of compute nodes, but as long as the storage is outside, you still hit the bottlenecks of I/O, right? Trying to get that data into the cluster is one of the biggest problems. So how was this solved? Again, 5-6 years back, when the interconnections were still 1 gig. And it's surprising, I mean, even today, interconnections between the servers are still, at places, they're still 1 gig, right? So the only way, or the best way to solve this problem was make sure that the data is right within the cluster. And this is basically what Hadoop is all about, right? You take your data, put it right into the server nodes, and then start utilizing the compute on those nodes to work with that data, right? So you're bringing, instead of trying to bring data into the compute node, you're basically distributing the application across where your data lives, which is, again, on the compute nodes. Now, because of this structure, there are certain use cases that are like basically well designed for Hadoop. For example, search, right? I mean, there's no other application out there, I guess, like when you deploy Hadoop at scale that can beat the performance that Hadoop provides. So I don't want to go through this whole MapReduce and what does map do, what does reduce do, but basically it's the idea is each node working on its own data in its own space and then coming up with certain results, which it sends across to the reducer over your network, and the reducers take care of collating, collecting that data, come out with the end result, right, based on how you define the maps and reducers. So the key concept here for me is like when we look at this, we kind of think in terms of what can I do on the compute side to optimize this cluster. But one of the prime factors is there's also movement of data across the cluster, which involves your network, right? And as much as people are focusing today on the compute side in terms of shall I use SSDs? How many cores do I need? How much memory can I populate here? You also need to think in terms of, okay, what is the actual interconnect between these nodes, right? And how am I utilizing it? Optimal, suboptimal. So moving on, few different job patterns that we see in Hadoop, right? And this particular patterns hold true for almost anything that exists today. So basically, one, you have a pattern where you're starting off with a large amount of data, but you end up with a really small resultant data. Like for example, if you search for, let's say, the popularity of, let's say, Hortonworks within the whole big data world, so search for it. Now, you might be dealing with petabytes of data going through all your web, whatever, right? But the resultant data would not be that big. And the second thing is like where you have data, the amount of data that you input to your cluster is the same amount of data when you, once you run the MapReduce job, you end up with the same amount of data in the end. Now, a third one is where you start off with a smaller amount of data, but you end up with large amount, like, normalization, things like that, right? So three different constructs, and the impact that they have on the network is completely different. In the first case, let's actually look at the data itself. In the first case, even though these are the three cases that we just discussed, even though in the first case it looks like there are really large spikes, actually that's a 1 gig line, and the spike is only 50 megs, so it's like nothing. So analytic jobs, the amount of data that's going across the network is almost limited, very little. But here's the thing, right? Often your SLAs are higher for those analytic jobs versus the other type of jobs which are like more batch oriented. You're starting with, let's say, a terabyte of data. You send, based on replication, 2-3 terabytes across the network, and you end up with another terabyte of data, or maybe 3 terabytes of data, right? I had an interesting chat with one of the really large web search providers, right? And they were saying like sometimes they use replication factor of 20 because they really want to make sure that a particular data lives. I mean, it's not lost, right? So in such cases, when you have that replication increase to that extent, right, the amount of data that actually goes across the network is huge. Now, the thing about that data, though, is it's not really SLAs are not that critical with that data versus the data where you have, like, really these what you call smaller queries, like high H-based queries or high queries. They don't cause too much network bandwidth usage, but they end up being more critical. Now, we like to call them like different kind of flows, right? What we are creating here. Like, so you have small flows all the way to large incast. Basically, small flows is your heartbeat messages, your, if you take like, H-based queries or high queries and things like that, versus large is your HDFS replications and all that. Now, having set the stage from a Hadoop perspective, right? Number one, to prioritize this, one of the things from a compute side, right? We have a lot of constructs on the compute side to prioritize certain jobs over certain other jobs. Let's take a quick look at what we have on the compute side, and this is going to be really basics. The reason is these constructs are applicable on the network And today, we don't really have a solution on the network side that actually helps you prioritize at this level. And I'm going to talk about those, what we have, the next generation networking technologies that I was talking about. I'm going to discuss them. So scheduling and prioritizing, very simple, right? Like, so you have some jobs, you have some cores available. You try to make sure that a particular thread or a particular job is scheduled on a particular core or a particular processor, right? So simple scheduling. And then when you want to reschedule, sometimes you want to reschedule a job. I don't want it to run on core 1, I want it to run on core 2. So you have mechanisms today on the compute side to shift it over, right? And this is per node, a single server. When you run a single server, you're able to schedule a job on a core, you're able to reschedule a job, and you're able to prioritize and deprioritize jobs using nice, renice, and certain other constructs, right? Now, this is great on the compute side. And again, like I said, this is only single node. If you go to a cluster node, and I've taken the example of Hadoop itself here, right? You have this whole concept of, resource management, node managers, and basically their whole job is to make sure when you schedule jobs, where are those jobs located, where are those jobs running, what is the priority of that job, there's a scheduler which is actually taking care of those constructs, right? Now, these constructs, like I said, are not really available today on the network side. The only construct that you have is something called QoS, and it has nothing to do really, unless you stamp the packets on the server side, which we are not doing today for workloads like Hadoop, it really doesn't do much. There are workloads outside Hadoop which involve large clusters like in high performance computing, where people are exploring ways to create this prioritization, but it's really not available today. Let's say we did have something like that available. Is this really useful, right? From a network perspective, is this really useful? Now, the next data set that I'm presenting, this we have seen in the past too, but basically what we're doing here is enabling QoS. QoS basically says, if I see traffic coming from this port to this port, and basically make sure that that has the highest priority, as simple as that, right? With simple QoS, setting up of QoS, you can see a 60% benefit with certain operations in HBase. Prioritizing network at network level helps your jobs. There is no question about that, especially when you have multi-tenant jobs, and that is where we are going towards, right? With Yarn, we basically want to use the same cluster for batch jobs, and also for in-memory tasks and several other things, right, like HBase, whatever else, right? And the SLA requirements are quite different for these two different aspects of workloads, right? So when you are dealing with such workloads, prioritizing, yes, compute side prioritizing is really important, but prioritizing at network, it helps too. And as I said, you can see it in the graph here. Now, QoS, while being really good and helpful, it's not trivial to set this up. Let me be honest, right? Like, so you have it available on probably just about any network out there, but it's not trivial to set it up, especially when you're dealing with large clusters like the big data clusters. So how do we solve this problem? Scheduling and prioritizing from a network perspective. Again, this is the next generation solution, right? What we have done here is, today, if I take a flow, right? Let's say in a data center, if I want to send, let's say, ingest or send some traffic from here to, let's say, some place over there, you select a path, you set a path, and then once it is set, it stays for the duration of that particular flow. It will only change if one of the devices in this path completely breaks down and goes away. Then you try to figure out a different path, but otherwise, based on hashing and all that, right? There's one single path set for a flow. Now, the actual components that make up a flow are packets, right? End of the day on the network, it's basically packets. You cannot go to a packet level and say, I want to send this packet this way, and I want to send the other packet this way, you know? The reason being, if the latency between those packets, those paths are different, you end up having like reordered packets, and the server starts thinking, man, maybe this is messed up, right? Maybe there are drops or something, and it starts, that basically messes up your application, right? So how do we solve this problem? So after a lot of research from both from Cisco's side, Google and Microsoft, there's a paper that's being published with SIGCOMM, and it should be out pretty soon, about congestion awareness. One of the things that we realized was flow is never constantly flowing. There are gaps in a flow. And give me a second. And there are ways to take care of, make use of those gaps. And what we are doing is take a flow and cut them down into smaller parts called flowlets. And with these flowlets, we'll see what we can do with these flowlets, right? This is concept number one. Today, traditional networks, they deal with only one single flow. And the only way to change it around is when it breaks down, right? Whereas what we're doing is break down that flow into smaller flowlets. And what can we do with it? We'll see in the next slide. Now, congestion awareness. This is the second concept, second problem that we have today with networks today, right? The network infrastructure today, the top of rack, for example, in this case, the leaf 1, let's say servers are, 32 servers are attached to leaf 1, another 32 servers are attached to leaf 2. Leaf 1 makes its switching and routing decisions based on what it sees from itself, right? In terms of if it sees a connection to spine 1, it thinks, great, I have a connection. If it sees a connection to spine 2, again, great. Now, the problem here is spine 2 to leaf 2, there is a congestion for, let's say, whatever reason. A link may have failed, or maybe there's a lot of ingest happening there, or some other reason, right? Leaf 1 is not aware of the congestion that is between spine 2 and leaf 2. This is the problem with today's networks. They do not have awareness across your data center in terms of congestion points. Now, moving further, a third point, right? Today's networks, unless you apply something like QoS, there is no way they can prioritize certain small flows over certain larger flows. Now, why do I want to prioritize small flows? Like we have seen in the previous slides, right? Ingest, replication, these turn out to be really long flows, right? Like it could be like 256, 512 meg, whatever, based on your block size. And it could be gigabytes of data based on how much flows are coming in, right? Like it depends, right? So those flows, they often do not have, again, the right, like high SLAs, right? Versus something like Hive or a NoSQL query again, right? What we've seen is in this small graph that I have here, we've sent a small flow, 128 kilobyte KB flow, right? It's like a small, really small flow. 128 KB flow kind of looks like a NoSQL database query, right? When we send that, a normal flow, that would have taken like 1.2 microseconds to get from point A to point B, could end up taking 70 to 80 microseconds if you had just 1 gig of traffic running on that same network. Now, with some of the folks offering services like platform as a service, right? Basically, they have a cluster of nodes, the same cluster divided across multiple customers. One could be running a batch job on the same top of rack, and another could be running a NoSQL job, right? And the NoSQL guys are really messed up because end of the day, they don't get priority at all because these jobs end up taking up all the resources that you can throw at them, right? So we need prioritization. Like I said, there's a way to do it. You could use QoS, but the problem with QoS is, again, how do you set up for large clusters, right? And especially if you're, let's say, a service provider, and you don't have really the view into what your customer is actually running there. All that you know is the customer says, no, this is not working out fine for me, right? So how do you implement those things, right? What we've done is basically at hardware level, being able to prioritize small flows any day, small flows against the large flows, right? Simple prioritization, that's it, at hardware level. Again, this is new, not existing in the previous, the traditional networks. This is something new that is coming from Cisco. So And finally, dynamic load balancing. I spoke about congestion awareness across the network, and I've also talked about a little about the flowlets, right? So how are these two components going to help? In a traditional network with ECMP, what happens is, since leaf 1 is not aware of the congestion between spine 2 and leaf 2, it starts sending data across both the links at the same rate, 50% across both the links, right? But what happens is, once it hits spine 2, where you actually have congestion, maybe a failed link, what happens is it starts, the spine 2 starts dropping, you have to resend the data. Often ECMP will again hash it to the same link, and you basically, that's a cascading problem. Till you fix the problem, there's no way it is going away, right? Now, what we've done with dynamic load balancing is, now since we are able to divide the flows into smaller flowlets, what we can do is mid-flow, take a flow that is going across spine 2, mid-flow transfer it to spine 1 without the server being aware that the path has changed. And basically with this, again, we need to be like really careful how we do it, right? Because end of the day, we do not want the packets again on the other side to be reordered and make a mess of it, right? So with flowlets, we are able to start spreading the flow, single flow, across multiple paths and make decisions based on congestion. Not only the existing flows, but when new flows start, you could also transfer those flows across. I mean, based on, you make a decision based on not simple ECMP, but based on the congestion levels across the network, which is really useful when you look at the networks today, let's say with multiple of racks, right, hundreds of racks. When you have a cluster of that size, it's really essential for your network to be aware of those congestion points and make the right routing switching decisions. Great. And finally, this is the well-known stuff. You probably would have seen it earlier too. But basically, the whole idea of buffering and Hadoop workloads being what they are, it's always useful to have a lot of buffer, but where? So what we have seen in our test cases, right? What we have seen is, in this particular test case, we have 2 top of racks and 1 spine, like 2 leaves and 1 spine. Now, the blue and the red is the buffer usage on the leaves, and the line that you can't see, which is like at the bottom of the graph, which is like in a light green color, that's basically the spine. And what you see is most of the traffic is absorbed, the real congestion points are absorbed at the leaf level. Leaf is the switch that is actually connecting to the your servers, whatever servers, where it is directly connected to the servers. And you can see this is one of the areas that you need to be aware of when you're making decisions regarding your infrastructure in terms of where is my buffer in this particular infrastructure. If you have like loads of buffer on your spine, it's not really going to help you with your big data workloads. It needs to be on the leaves. Okay. Now, so much for these concepts. So what are the benefits that we can derive from this, right? Are there workloads that we've seen? So this is, I need to mention one thing right in the beginning, second slide, I'm going to again put up to. We have this site called cisco.com, Go Big Data. Basically, please go take a look at that page, because we have a lot of data on a lot of these workloads that we have been testing, and some of the data that we test, we are also going to port there. What I'm covering is just a few test cases and how it looks, but you have a lot more data there. So we're using 2 topologies here. These are Nexus 9Ks. This is the next generation switching platform from Cisco for the data center. And you have like 2 leaves and 2 spines on top. And in one case, I have all the links connected and working fine. In another case, I have one of the links down to create an asymmetric network. And let's look at the results. So One with Memcached, which is kind of similar to your H-based NoSQLs or whatever, right? So what you're looking at here is like we started Memcache with a compute node where nothing else is happening, right? It's just Memcache. And you see like, 160 megabytes per second. Of course, that's not the, I mean, throughput would have been better. But basically, the idea is it is running at 160 megabytes per second. But the moment we start a large flow, in this case, we emulate large flows with data from iPerf. What happens is the iPerf data, the flows, start using up your network resources, and within no time, the Memcached D's what you call throughput, right? It just drops drastically. So on the network side, we basically enable packet prioritization, dynamic packet prioritization, which we discussed earlier, right? Which is basically make sure your small flows have priority over the large flows on that network. And as you can see, it gives you what you call a benefit when it comes to the performance. Now, it's not again 100%. The thing is, we are looking only at the network side here. You also need to take care of the compute side in terms of prioritizing those Memcached threads or your H-based threads on the compute side. Maybe lock it down to a core or something, and maybe make sure it has the right nice value and things like that, right? There are things that you can do on the compute side too. But what the point here is just by enabling, just by making sure that the small packets have priority, you end up seeing a huge boost in the performance of these. And it's not new. We've seen this earlier too with the QoS. When we enable QoS for H-based workloads, you see a huge benefit there too. It's basically making sure that network doesn't become a point of what you call a kind of a bottleneck or increase the latency of your NoSQL queries. ECMP versus dynamic load balancing, right? With asymmetric loads, and again, I had in this summit, I was talking with someone here, and basically he was saying, he looked at this data and he was saying like, when a work or a job fails, right, for them, you start having a backlog of jobs because you are basically on a schedule. I want to run this job at this point, this job at this point, right? When job fails, now you have to get into this backlog mode, and how do you get whatever your backlog jobs are done and move on to the next thing, right? So he was saying like they end up having like 4 to 6 hours of backlog. Why? The reason is when you look at ECMP versus DLB, ECMP, because it is distributing traffic equally across without considering the congestion point, your traffic starts dropping, right? Whereas in the dynamic load balancing case, what we are doing here is we are transferring data 66% on one side, 33% on the other side, right? Considering the congestion point here. And because of that difference in the way we transfer the data, what we see is when you have link failures, and again, it could be congestion. If it is a link failure, it's even more worse because often link failures are not corrected the very instant, right? You need to have somebody go there, take care of it. Maybe it takes a day, maybe it takes 2 days or whatever, right? So while that is in that state, you have all jobs being basically impacted, whereas with dynamic load balancing, it takes into consideration the available bandwidth across your network from other parts and make sure that this congestion does not impact the job completion time. So moving on, those are some of the things that we're bringing into the network space, and please come down to P12, booth P12 to discuss more. Let me quickly go through a few more things. We have a few more minutes. So visibility plugins, like one of the things that we keep thinking about, right? Like how do you get cluster related information from within the switch? So basically having the ability to see what kind of jobs are running in your cluster, what kind of jobs are what kind of load it is causing on your network, how do you correlate it for a network admin from inside the cluster, right? We spoke about it last year, And in this particular version, again, we're going to post this on GitHub. Like this is all going to be open source stuff. Because end of the day, this is Python scripts that are basically talking to your Apache Hadoop cluster and getting this info, right? And you could modify it to talk to just about anything, like HBase or whatever else, map or like a completely different workload, right? You could get that data in. So open source, so you can modify it as much as you like, the way you please. There's nothing what you call closed here. It's not hidden in some CLI. You know exactly what is happening here behind the screen. So, so you can get job-related information, buffer-related information, all kinds of things. And every session, we kind of like to bring in a different graphing tool, right? We saw RRD tools in the past, and we've seen like Cacti and Nagios. In this case, I'm using Graphite. Basically, send all the data from your switches to your Graphite tool, and it's a very simple way to graph so that you have a historic data of what's happening with your cluster. And also instantaneous data of what's happening right then and there, so the your network admin has one more tool to use when he's troubleshooting issues. Optimization and tuning, couple of things, just two things that we'll take a quick look at. One is SSDs. A lot of people are thinking about using SSDs in the Hadoop clusters, right? Does that help at all? So with Terasort, what we've seen is, and Terasort is like the worst benchmark that you can use on Hadoop, right? Because Hadoop, I mean, there are like other workloads that Hadoop really excels at. But even with Terasort, you see like 18% what you call better performance, or with non-SSDs, you lose 18% performance. Second thing is, this is one more really interesting parameter within the Linux clusters, and basically huge pages, right? Transparent huge pages. When you enable them, you see a huge spike in performance, like 33% spike in performance. This is something that you could try out and see. And this one is actually, I mean, it works great for Hadoop clusters, but you could try it out on other applications too. It's really useful. Finally, recommendations. So this is something that we've seen just to make sure that, I mean, just to kind of close it, right? What are the things that really matter with Hadoop clusters? As we move towards the in-memory databases and all, maybe latency would start becoming a little bit more useful, and that is the reason why we have QoS and packet prioritization and all that. But really, end of the day, for Hadoop clusters, like when you do batch jobs and all, the number one factor that you need to consider is availability, and also add to it the load balancing that I was talking about. The second factor is buffering, and then you have oversubscription and the rest of the things. But availability, number one. Make sure the nodes are dual attached, you're using dual connections and port channels, whatever else you can get to, so that a single failure doesn't take your cluster down. Because again, these failures are cascading. A single failure in our cluster, what we've seen is increases the time taken by 4 times, right? Now, one thing to consider here is this job is a really small job, a 10-minute job, right? So because of the way the heartbeat works and because of the time it takes to detect a failure and recreate and rerun the job, what we see is like it increases the time taken to finish that job if you happen to run it on the, I mean, like if there's happens to be a failure. So number one factor is like make sure it is redundantly attached at multiple points. Finally, data node speeds, right? It's interesting, like some of the clusters are still at 1 gig, but the thing about those clusters is that they're still using like, maybe 4 drives or 8 drives, right, the max. Whereas most of the enterprises who are starting today, you start with like, 24 to 32 drives, and often those are SSDs. When you're looking at a network of that nature, of that size, right? Please use 10 gig, because even though it looks like 10 gig, it's only 40% utilized. What happens is You could use the rest of the bandwidth for optimized flows and also for ingest, egress. I mean like importing the data, exporting the data, and it helps. Like if you try to use replication factors like crazy like 20 or something, it really helps to have a network that is capable enough to take care of such replication factors. Also to consider is when a rack fails, you would have all kinds of balancing going on where you still need to have that data going across your nodes and make multiple copies again with the rest of the cluster, right? So those kind of things, you really need to look at the network and have the right kind of network to take care of that. Finally, we have a lot of data, like I said. This is just kind of a sampler or appetizer or whatever you call it, right? So this is just a small part of what we have there on Go Big Data. So if you please do take a look at that site, and you'll find lots of useful information there. And we'll also be, we are actually running through a lot of testing using various vendors like Hortonworks and Cloudera and Mapper, and we would be showcasing, like presenting whatever we find, what our recommendations are again on this site here. So please do go to that site, please do visit and take a look. Also, we have a small Cisco passport program. Please come down to our booth in P12 if you would like to, if you are interested in something like Beats audio, Beats headphones. Any questions? Thoughts, ideas, concerns? Wow, so it all makes perfect sense and you understand it perfectly. That must be really good. Going once, twice. All right. Thank you so much. You've been a great one.